another recording of a solving a problems from chapter 5. This is a very important chapter, and I'm going to do problem 8, which is paired with problem 19 and problem 20. So what it's given is a simply supported beam. It's flat, width 60 millimeter by 12, and it's loaded 175 millimeter from one end. Full length is 450 millimeters, with a load that varies from 1450 to 140 newtons. And we need to calculate the stress ratio R, minimum stress over maximum stress, for problem 8, and then from problem 19, the materials given SAE 1020 hot rolled steel, and we need to calculate design factor. And on problem 20 says propose an alternative design for the bracket to achieve a higher design, a lighter design with design factor approximately 4. I'm not going to emphasize this. Would be a matter of increasing the area moment of inertia, make it more bend resistance. Really, if you flip the flat and to have it 60 millimeter height and 12 millimeter wide, so if you rotate 9 degrees, it will be much stronger in bending. Okay, so let's look at problem 8. We say, I want to make sure the door is closed. It is, it's just background noise, sorry for this. Okay, so what we need to do is to calculate the, or draw the load diagram, shear force bending moment diagram. Maximum bending moment will be at the load, we know this very well. And we're going to calculate the stresses for the minimum maximum load. Okay, so problem 5.8, and we have the beam. Again, it's simply supported, and this is the load F, and we have 175 millimeters, and we have 275 millimeters. Reactions at the supports. We can, of course, some moments about points which are not labeled, although there's an AA cross section. So it's 60 millimeters by 12 millimeters. Okay, so the reactions at the supports, let me call this A, B, and C, irrespective of that cross section with arrows to the side. Okay, so this will be F times 275 over full length, which is 450. And this is going to be F times 175 over 450. This is a result that I remember from other analysis. If you're summing the two forces, it's verified. It's going to be the F value. Now F has two, or is going to be F. F has two values. We know this. It's 1450, 140. So we're going to solve the problem parametrically, and so draw the diagrams parametrically. The shear diagram V, will be newtons, will be the larger value here and a draw by f, and it closes to 0. So plus and minus. This piece is, let's see, if we're to write 275 by 450, 275 450. Okay, so 275 25. So 275 over 25, that's 11. So f times 11, and 450 over 25, it's 18. This other one is going to be, so positive, negative. This other one is going to be f time in negative value. So 175 over 25, that's 7 over 18. And then moment diagram, Newton millimeters. It's going to be like so. So okay, so the maximum value is going to be the area 11 over 18 times 175. 11 over 18 times 175 equals so this is well, we work with fractions, so 175 times 11, okay, 1925 over 18 f. Okay, positive moment. Same should be if we go the other way. So area under this, or of this rectangle, is 7 over 18 times 275. Same value. Okay, so we have the moment diagrams. And now we can calculate sigma min and sigma max. Sigma min is going to be m minimum over the section modulus. And section modulus for a rectangle, I'm at the back of the book, appendix 1, and S about x is the width times height squared over 6. So I have capital B, nothing to do with this B here, of course, and then the height H is 12. So Sx is BH squared over 6. And what we have F min. F min goes with I can 1925 over 18. And then B, we said it's 60 times 12 squared over 6. And let's calculate. So F min, to make the second part easier. So 1925 over 18 times 6 over 60 over 12 over 12 equals, so times 0.07427. I'm just going to put this in the memory. So one more time, 1925 times 18 over 60 over 12 over 12 times 6. Mistake. So 1925 over 18, and then over 60 over 12 squared times 6 equals. So I got the same this time. And these will be megapascals because I worked with newtons, or for force in newtons. And again, the minimum value is 140. And then sigma max is going to be F max times 0.07427 megapascals. Okay, I'm not yet at E, so let me check one more time this whole thing. 1925 over 18 over 60 over 12 squared times 6 equals. Okay, and then put in the memory times 140. This is 10.4 megapascals, the minimum value, and then the maximum value would be the same thing times F max is 1450 newtons. Okay, so times 1450, and this is 107.7 megapascals. Okay, so we have the min-maximum stresses, and we said that the R, the stress ratio R, is sigma min over sigma max, and I'm dividing this, which I still have it on the calculator, by 10.4. So over 10.4 equals, and I take the inverse. So it's 0.0966. So this was what problem 8 required. Okay. So we've got problem 8. Problem, the companion, problem 19, it gives the material, it's SAE 1020 hot rolled, and we need yield strength and ultimate strength for this material. Condition, again, it's hot rolled, and we want to calculate the design factor N for fatigue loading. We look up at the back of the book the properties of 1020. We've been on that page before. Properties of design properties, carbon and alloy steels, and 1020 hot rolled is, we're working with megapascals, so it'll be 207 and 379. Megapascals. And again, condition finish is hot roll. What I also want to calculate is, because it's a mean alternating stress diagram, so we want to calculate sigma mean, and sigma mean is going to be sigma, the minimum value of sigma plus sigma max divided by 2. Sigma alternating is going to be sigma max minus sigma min divided by 2. Okay. And with the two values here, so I have 107.5 plus 10.4 divided by 2 equals, that's 59.1 megapascals. And the other one, the alternating, is going to be 107.7 minus 10.4 equals, that's 48.65 megapascals. So I have the mean value and I have the alternating stress value. We're going to make use of these. Yeah, this penetrates the page. There we go. It transmits through the page. One thing I could do is just not to spoil too many pages, is to do this. Okay, so problem 519. I'm also going to produce the sigma mean, sigma alternating stress diagrams. And what do we have? We have, and you could work this at or draw this at scale. Also have a spreadsheet. I'll share it with you. A spreadsheet to automatically calculate the design factor when you know the load point. So let's see. We have on the diagram there will be yield strength. We've got it. Ultimate strength. We've got it. The true endurance limit, we need to calculate it. There's no stress concentrator, so we need to calculate the true endurance limit, Sn prime. Sn prime. And prime actually goes above. So Sn prime, this is equal to procedure for estimating actual endurance limit, Sn prime. So it's going to be the endurance limit corrected for surface finish. And we have the hot roll condition, and the ultimate strength is 379. So 300 and 350, 375, 400 megapascal. So I have it right here, and hot rolled again. So what I'm reading is about 150, 140. Okay, so 140 endurance limit corrected for surface finish. And the entire equation is Sn times these coefficients, the material factor, the type of stress factor, the reliability factor we need to discuss about, and the size factor. Okay, so we figured one already from figure 511. I said that at SU 379 for the hot roll curve, we on or off the hot roll curve we read like 140 megapascals. So this is 140 megapascals. The material factor, it's work steel, so this is 1. And then the type of stress factor, it's 1 because I have bending, we have bending. The reliability factor, 50% reliability, it's a bit too small. So let's go with a 90% reliability. And for that, we increase or rather the coefficient goes down from 1, which corresponds to 50% reliability at 0.9. And then size factor. Now size factor, this is not a round bar in reverse bending, but rather a rectangular section that is flexed. So the equivalent diameter, we calculated equivalent diameter. This is equation 575 on page 182. So equivalent diameter is 0.808, and it says square root of h times b. Now elsewhere, for the back of the book, for area property, notations were capital B and capital H. Okay, so H is 12, B is 60. The equivalent diameter is 12 times 60 square root times 0.808. So it's 21.68 millimeters. So for 21.68 millimeters, I turn to page 181. We can use this graph, or we can use the table 5.4. Let's use table 5.4. So the equivalent diameter is between 762 and 50. And so CS is going to be equivalent diameter. The equation, it's just uses D, but ours is equivalent. It's over 762 at power negative 0.11. Okay, still have the equivalent diameter, so divide by 7.62, put it in the memory, just in case. And then going to power 0.11 negative equals. So again, I'm having put the wrong number. 21. One more time. 21.68 over 7.62, and I raise it to the power 0.11 and negative equals. All right. So the value is 0.89. Let's see, is it confirmed if I use this chart? So I have 0, 25, and I move up, yeah, slightly less than 0.9. So the graph confirms the equation. So I have all the, I'm ready to calculate true endurance limit. So this is in 0.89. So true endurance limit, it's going to be 140 times 0.9 for reliability times 0.89. So it's 112 megapascals. I gave up the fractions, 0.14. Okay, so we have everything, and we could now plot the mean alternating stress, and we're going to use the Goodman line. Again, stress concentration factor is 1, and don't forget the equation on the figure it has a typo to it. So, and I'm confusing my camera, so this shouldn't be dividing sigma m, shouldn't be SY, but rather SU. So the mean alternating stress diagram, again, you could work it at, you can draw the scale, and you can extract the design factor from the graph by measuring, similar to modify more method. The points that go on the diagram are the yield strength. So let's see, if I have we'll work with millimeters. So okay, could have started with the a bit larger area of the paper or a new blank page. So if I have if I choose a scale factor of 0.2, what do I get? So 379, I'm going to place the ultimate strength on the graph. 379 times 0.2, I said 75.8 would be here. So this is 379 and it's the ultimate strength. And then I have the yield strength is 207 times 0.2, that's 41.4, 1.4, and this is 207. These are megapascals, and it's yield strength. And I also place 41.4 on this graph, on the vertical axis that is, and this is 207 and it's SY. I have the yield line. I don't know how good this 90-degree angle is, and my lines were okay, could have done better. And then I have to also place on the graph the true endurance limit, which was 112. So 112 times 0.2, that's 22.4. 22.4 right there. So this is 102 and this is Sn prime. And I'm connecting for the Goodman line, I'm connecting the two. That is Sn prime with Su. Failure zone is, or rather safe zone, is going to be what is inside of this four-sided polygon. I have 0, 0 here, origin. Let's put on the graph the mean and alternating stress values, these two, corresponding to the load point. Remember, modify Moore theory for brittle materials. So we have 59.1 times 0.2, that's 11.82 millimeters, almost 12 millimeters. So this is sigma mean, and it's 59.1 megapascals, and then 48.65 times 0.2, that's 9.73, almost 10. So this is sigma alternating, and it's 48.7. Okay. Again, using drawing instruments, high resolution figure. You of course achieve better accuracy. And so we have the load point now of coordinates sigma n, sigma a. I'm connecting it with the origin. And so load point, load line and this will be the failure point. Okay, and we can measure on the graph so measuring on the graph, it will be like 26 millimeters on the figure divided by 15. 26 over 15. And it's 1.73. Again, pretty inaccurate. I drew the line by hand. Resolute could have made the figure full page. So this is graphically with all the imperfections. But we can use the equation or equations, Goodman criterion. And from the figure, we can tell that the intersection happens with the Goodman line rather than the yield line. But we can verify. So we can calculate, we're going to calculate design factor using both, and of course retain the smallest of the two. What is the significance? One equation gives you the design factor intersecting the Goodman line. The other one gives you the design factor intersecting the yield line. If the intersection happens with the Goodman line first, n resulting from the equation 528 will be less than n resulting from equation 529. So let's see, I have equation 528 and kt again is 1, so I have sigma a over Sn prime plus sigma m over Su equals 1 over n. Or, so sigma a is 48.65, Sn prime is 112 plus sigma mean is 59.1, sigma u is 379, and what do we have? It's 48.65 over 112 plus 59.1 over 379. So this is 0.5903. And if I take the inverse, I get n 1.69. Wow, pretty close. If I'm now using the yield equation, intersection with the yield line, or checking for early cycle yielding, the equation is sigma a over Sy plus sigma m over Sy equals 1 over n, and we have 48.65 plus 59.1 over 207. And so 48.65 plus 59.1 over 207 equals 0.5205. And from here, and this is 1 over n, so from here I had n is a bigger value, 1.92. Okay, so this was equation 529. Okay. Of course, the answer to the problem is, we agreed, this smaller value, and should have been very close to the one calculated graphically. determined graphically, provided that you do it carefully with drawing tools, and make sure high resolution figure, full page. You can use chalk and draw on asphalt on a driveway, but make sure that the angle is not. It's not that bad. Appear worse earlier, which is visible. I mean, the numbers are pretty close to each other. Okay, so this was problem 19. I said problem 20. It's a design problem. By just looking at the figure, you have this flap, this beam, and it has reduced moment of inertia, bends quite a bit. If you look at the early analysis, so we had the equation for S, the section modulus. The higher, the bigger H, the bigger the section modulus, the smaller the stresses would be. So a quick answer to what problem 20 requires is to just increase the thickness and reduce the width of the beam, and we can even use this diagram. So if you want to make the design factor 4, like they said, you need to move the load point inwards towards only like somewhere here where I have the ratio. So you measure what would be, if I want n to be 4, then the load point has to be at so it has to be at 26/4. That's at I say the wrong thing, so I need to have this is 4, so if I'm to calculate this, yeah, 26/4, that's 6.5. So I measure 6.5 millimeters. This should be the load point for 4 design factor. And you can go in reverse. You can look at the mean and alternating stress, new mean and new alternating stresses, read from the diagram. And then you can calculate the minimum maximum stress, and you can find the desired S. Okay, so you get the new alternating new sigma mean new. You read them from the graph, and then you can go in reverse. You know the mean and the alternating. You can solve for minimum and maximum from these two equations. Minimum maximum stresses, force is the same, so you ultimately calculate what the desired section modulus is, and you have two variables to play with, B and H. You also want to minimize the volume of the material used to minimize cost. All right, so I guess our emphasis was on the analysis side, problem 5 and 19. If you can do analysis, you can do design, you just iterate. You can go back, you can put all these equations in a spreadsheet, and you just start changing B and H, even material value. If you were to do this for hire and it's, cost saving are primordial, you spend the day refining and going for the least expensive solution to the problem. Okay. All right, so this was it. 40 minutes of recording. Thanks for watching. I'm going to put them like I did before to where you can see them at the end. Page 1 and page 2. Okay.